folks, and welcome to this lesson on cell potentials and spontaneity. By the end of this lesson, you should be able to describe the structure and importance of the hydrogen half cell and calculate cell potentials using standard reduction potentials. Alright, to quickly recap, we're going to go over standard reduction potentials, and those are the potential energy differences in a reduction reaction. These values are always going to be based on just the reduction half reaction, and there are plenty of references that you can use to find these values. You can have positive values and you can have negative values. The ones that have positive values are when your electrons are releasing energy. All of these values are comparison to something else, and we'll talk about that in a moment. And we're looking at standard conditions. If we're looking at concentrations of solutions, they are all 1 molar. The pressure conditions for any gases are 100 kilopascal, and the temperature is always going to be 25 degrees Celsius or 298.15 kelvins. Alright, let's talk standard hydrogen electrode. Also can be reduced or simplified to SHE, but usually when you speak of it, it's always standard hydrogen electrode. So the standard hydrogen electrode uses this specific half reaction, and this is a basis for comparison with all of the other reduction reactions. So this is the one where you have that E0 value of 0. Any reduction reaction that happens better, easily, more spontaneously is going to have a positive number. Any reduction reaction that happens less spontaneously is going to have a negative E0 value. Now, as you can see, you have a solution and then you have a gas. And if we're using electricity, you're going to need something solid to connect to the wires that are going to happen. And so you're going to have to also have a passive electrode in here, which is usually going to be something like platinum or palladium. So the setup is going to look something like this, and we're going to pretend that it's connected to some other half cell later on, or further down. So we have our passive electrode of platinum. It is in a solution, and this solution is going to have some kind of acid in there because we need those hydronium ions. So we need some kind of acid that's going to give you a 1 molar concentration of the hydronium ions themselves. Now the other ion is going to depend on everything else. We could use a hydrochloric acid in this particular case, in which case your chloride ions would have a concentration of 1 molar too. Now in terms of the gas bit, you're literally going to have a tube that runs into everything and will keep on blowing hydrogen along the surface of that platinum. This hydrogen is going to be at a pressure of 100 kilopascals. So again, how do you do this comparison thing? Well, you build this electrode, and then you build another electrode that has the other half reaction that you're interested in. You connect it all up, and then you see which way the electrons are moving. If it's moving one way, then you're going to have a positive value for whatever is in here. If it moves the other way, then it's going to have a negative value. So once again, for a spontaneous reaction to happen, we need E0 values or overall E0 values to have a positive value. If it is not positive overall, then this reaction isn't going to happen on its own. You need to push in energy for that reaction to happen. To find out what the E0 value for the entire cell is going to be, you're going to take the E0 value for the half reaction, the reduction reaction at your cathode, and subtract it by the reduction potential of your anode. Please keep in mind when you're using this particular equation, you are taking the reduction values for both cases. Also, something to keep in mind when you're looking at this lesson or anything from the next one on reactivity, when you have a redox reaction, or if you're trying to have a redox reaction happen, you will need both a reduction reaction and an oxidation reaction. If both of them are reduction, that's not going to work. If both of them are oxidation, that's not going to work either. So let's take a look at this example. If a galvanic or voltaic or primary cell were constructed from chromium, iron, chromium 3 sulfate, and iron 2 sulfate, what is the standard potential of this cell and what is its spontaneous direction under standard conditions? So the likely half reactions that can happen with this situation, or the likely reduction reactions that you can get from this, are the one where you get the chromium 3 plus to the chromium, and then you have the iron 2 plus to the iron. Now I say the likely reactions that will happen here are those two, but don't forget the fact that chromium and iron are both multivalent, and so there are actually a whole bunch of other reduction reactions that are theoretically possible. But more about specifically what reactions are supposed to happen or would happen on the advanced reactivity lesson. So here we have our values, and if we are going to have an actual primary cell happen, we need an overall E0 value that is going to end up being positive. So if we take a look at these two values, both of them are negative at the moment, which isn't great, but again, both of these are reduction reactions. So we need one of these to be an oxidation reaction, and we need to see if it becomes an oxidation reaction, can we get an overall positive value? So I'm going to go over the determination in two ways. The first is using the equation from the slide we had right before. So E0 of the cell is going to be E0 of your cathode minus the E0 of your anode. And so can we get a positive value doing this? And the answer is yes. If we take the cathode to be the iron one, then we're going to have negative 0.45 volts. And we subtract it by the reduction potential of our anode, which would be the other one. It would end up being 0.74 volts. That will give you a positive value. Now, alternatively, another way that you can look at this is, since you have to find the overall reaction anyways, why don't we take the equation that we know is going to have to become the oxidation reaction and then flip it. So in this particular case, if we're going to take these values and we're going to add them together, we know that if we want a positive value, we need to take this reaction and flip it. Because otherwise, if you flip this one, you're going to get a negative value when you add these two values together. So here is our oxidation reaction. We're going to take our reduction reaction in this cell and write it down as is. And then if we're going to write the overall reaction, is going to be this. Now note that we did have to add in some coefficients while we were balancing that redox reaction, but also note that our cell potential doesn't actually change even though you have to multiply some of these reactions by a coefficient to make it balance. That's because, yes, you may need more of the electrons to have everything balanced, but the potential energy of those electrons doesn't actually change. So these reactions as they are aren't actually going to change the potential differences, though something that will change potential differences are things like pressure and concentration, which is why it's so important that those standard values are in standard conditions. And you have to make sure whenever you're doing any practice problems and you need to make these calculations, it is under standard conditions as well. More on that in a later lesson. That's the end of this lesson. I'll see you next time.